What if I told you that every click, every message, and every password traveling through your network can be captured live? Welcome to Wireshark, the tool that lets you see everything that happens on your network in real time. In this series, I'll take you from absolute beginner to professional level. So by the end, you'll understand how data really moves across the internet. So, what exactly is Wireshark? Wireshark is a packet analyzer. That means it captures network traffic, the data that devices send and receive, and lets you see what's really going on behind the scenes. Imagine it like an X-ray machine for your network. It shows you the hidden layers of communication that normal users never see. But here's where things get serious. Wireshark doesn't just show you random packets. It can reveal passwords, cookies, IP addresses, DNS requests, and even unencrypted messages if the traffic isn't protected. That's why professionals use it for network troubleshooting, malware analysis, ethical hacking, and incident response. But used the wrong way, it can also invade privacy. So this course is for educational and ethical purposes only. Always analyze traffic that you own or have permission to capture. Let's open Wireshark. Once you launch it, you'll see all available network interfaces. These are your device's connections: Wi-Fi, Ethernet, virtual adapters, and more. To start capturing, just select your active network, usually Wi-Fi, and click the blue shark fin icon. Boom! You're now seeing live network traffic. Every line here is a packet, data moving in and out of your computer. You'll notice columns like time, source, destination, protocol, and info. We'll break each one down in the next lesson. What you're seeing now is raw power, real-time insight into how your network breathes. In the next part, we'll cover how to install Wireshark properly on Windows, Linux, or macOS, and how to start your first clean capture. So if you're ready to see deeper, make sure you subscribe, because this is just the beginning of your Wireshark journey. Part 2. Install Wireshark, Windows, Linux, macOS, quick setup, plus first capture. In the last video, we discovered what Wireshark sees, and why it's one of the most powerful tools in cybersecurity. Now it's time to install it step by step and start your very first live capture like a professional network analyst. By the end of this video, you'll have Wireshark fully running, no errors, no confusion, ready to capture your first packets. Part 1. Installing Wireshark on Windows. Let's start with Windows. Open your browser and go to the official website, https://www.wireshark.org/download.html. Always download from the official site. Never third-party sources, because fake versions may contain malware. Click on Windows Installer, 64-bit, to download the setup file. Once it's done, open the installer. You can leave all default options checked, but pay attention when it asks to install PCAP. PCAP is the packet capture driver that allows Wireshark to see your network traffic. Without it, Wireshark can't capture packets, so make sure it's checked before continuing. After installation, open Wireshark. You should see a list of interfaces: Wi-Fi, Ethernet, loopback, etc. That means your installation worked perfectly. Part 2. Installing Wireshark on Linux. For Linux users, open your terminal and type this command: sudo apt install wireshark-y. If it asks whether non-root users can capture packets, select yes. Then add yourself to the Wireshark group using sudo usermod-a-g Wireshark $user. After that, reboot your system. Once you log back in, Type Wireshark in your terminal or open it from your app menu and you're ready to capture traffic. Part 3. Installing Wireshark on macOS. On macOS, you can use Homebrew. Just open Terminal and run. Brew install Wireshark. During installation, it may ask to install the chmod BPF package. This allows Wireshark to access the network interfaces. After installation, open Wireshark from Launchpad. And that's it. Simple and clean. Part 4. Start your first capture. Now it's time to start your first real capture. Choose your active network interface, then click the blue shark fin icon at the top. You're now capturing live traffic. Each line represents a packet moving across your network. Look at the columns. Number. The order packets were captured time. When they arrived, source, who sent the packet destination, who received it protocol. What kind of communication it is, like TCP, UDP, DNS, HTTP, info, extra details about what's happening. When you're done, click the red square icon to stop capturing. You can now analyze the packets, apply filters, and see what's happening behind every website, app, or connection. Part 5. Wrap up and hook for next episode. You've just completed your first live capture. Welcome to the world of packet analysis. In the next video, we'll unlock the Wireshark interface, the layout, menus, filters, and hidden tools that turn you into a professional packet hunter. So if you're serious about mastering Wireshark, hit that subscribe button and get ready, because in Part 3, we dive deep into the GUI and start using display filters like a real pro. Part 3, First Capture in Wireshark plus display filters, step by step. Welcome back, Cyber Warriors. In the last episode, we installed Wireshark and made our first live capture. Now it's time to understand the Wireshark interface and master display filters, the secret weapon of every professional network analyst. Part 1. Understanding the interface. When you open Wireshark, you'll see 5 main sections. Menu bar, where all tools and settings are located. Toolbar, quick actions like start, stop, save, and filter. Packet list. Each line here is one packet captured. Packet details. This shows the structure of a selected packet, Ethernet IP TCP data. Packet bytes, the raw data of that packet in hexadecimal and ASCII. These 3 panes work together. Select one packet, and you can inspect its full journey from your device to the destination. But when you're analyzing hundreds or thousands of packets, you can't scroll forever. That's where display filters come in, to show only the traffic you care about. Part 2. Display filters. Deep dive. Display filters are typed into this bar at the top, right here. They help you focus on specific types of packets. Let's go one by one IP. Show only IPv4, traffic IP. This filter shows only IPv4 packets. IPv4 is the most common version of the Internet Protocol. It defines how packets are addressed and routed between devices. Use this filter when you want to ignore other protocols like ARP or IPv6. For example, if you only want to analyze standard Internet communication, type IP and press Enter. Instantly, you'll only see IPv4 traffic 2. IPv6, show only IPv6 traffic IPv6. This filter displays only IPv6 packets, the newer version of IP that supports longer addresses. Use this when analyzing modern networks or testing IPv6-enabled devices. 3. TCP, show only TCP traffic, TCP. TCP stands for Transmission Control Protocol. It's reliable, connection-oriented, and used by most web traffic like HTTP, HTTPS, and FTP. Use TCP when you want to analyze websites, downloads, or login sessions. You'll notice sequence numbers and acknowledgements. These are signs of TCP's Reliability System 4. UDP, show only UDP traffic. UDP. UDP stands for User Datagram Protocol. It's faster but less reliable than TCP, often used in streaming, gaming, or DNS queries. Use this filter when checking VoIP calls, game packets, or live streams. 5. HTTP, show only web traffic, non-encrypted, HTTP. This filter shows only HTTP packets, unencrypted web traffic. It's great for learning, but remember, in real life, most websites use HTTPS, so you'll rarely see plaintext data unless testing in a lab environment. 6. DNS, show only DNS traffic, DNS. DNS, domain name system, converts domain names like google.com into IP addresses. Use this filter to analyze domain lookups, find suspicious requests, or detect malware contacting strange domains. 7. ICMP, show only ping packets, ICMP. ICMP is used by ping and traceroute commands. This is useful when testing connectivity between two hosts. Example, run ping 8.8.8.8 in your terminal and filter with ICMP in Wireshark. You'll see echo requests and replies. 8. ARP, show only ARP traffic. ARP, Address Resolution Protocol, helps devices map IP addresses to MAC addresses inside a local network. Use this filter when diagnosing local network issues or checking for ARP, spoofing attacks, 9SSL or TLS. Show encrypted HTTPS traffic TLS. This shows all encrypted HTTPS traffic. You can't read the data here unless you have the encryption keys, but you can still analyze patterns, like which domains are being accessed or how long connections last. Bonus tip, combine filters. You can combine filters for powerful searches. Example, show only TCP packets to or from a specific IP. TCP and IP.ADR equals 19 and 2.168.107.100. Or show only DNS requests from your device. DNS at an IP.src equals 192.168.107.100. The possibilities are endless. This is where true packet mastery begins. Part 3. Saving your capture. When you finish a capture, click File, Save As, and save your file as .pcapng. This allows you to reopen and analyze it later. Part 4. Wrap up and hook for Part 4. You've now mastered display filters, the heart of Wireshark analysis. In the next part, we'll go deeper and learn packet structure, from Ethernet IP TCP payload, the anatomy of every packet you capture. This is where your understanding transforms from user to professional analyst. So subscribe, stay sharp, and prepare for the deep dive. Part 4. Packet Anatomy, Ethernet, IP, TCP/UDP, and Payload. Wireshark explained. Welcome back, warriors of the network. In the last episode, we learned how to capture live traffic and filter exactly what we need. Now, it's time to dive deeper into the anatomy of every packet, because if you truly want to master Wireshark, you must understand how data travels, layer by layer, from your device to the destination and back again. Part 1. The OSI model reminder. Every packet follows a layered model called the OSI model, Open Systems Interconnection. It's divided into 7 layers: physical data link, network transport session, presentation, application. Wireshark mainly shows us layers 2 to 7 because that's where all the meaningful data lives. Part 2. The packet's journey, step by step. Let's select any packet in Wireshark, for example, an HTTP or DNS packet, and expand its details section. You'll see the structure clearly divided: Ethernet, IP, TCP, or UDP payload. Let's break these down one by one. Ethernet layer, Layer 2, data link. This is the lowest visible layer in Wireshark. It's responsible for delivering packets inside the local network, LAN. It contains 2 important fields: source, MAC address, your device's network interface ID, destination MAC address, who you're sending the packet to. These are hardware identifiers, not IPs, and they never leave your local network. Attackers sometimes spoof these addresses, so knowing where to find them in Wireshark is critical for forensic analysis. 2. IP layer, Layer 3 network, Internet Protocol version 4, destination IP and source IP. The IP layer defines how packets move between networks, from your LAN to the Internet. It contains source IP, your local or public address, destination IP, the target server, TTL, time to live, prevents infinite routing loops, protocol, indicates the next layer, TCP, UDP, ICMP, etc. If you ever see an IP packet without a valid source or destination, that's a red flag for possible spoofing or misconfiguration. In analysis, this layer is where you trace who's talking to who. 3. TCP or UDP layer. Layer 4, transport. For TCP. Example, Transmission Control Protocol, SRC port, 50,850, DIT port, 80. TCP is reliable and connection-based. It ensures data arrives in order, without loss. You'll see fields like source port / destination port. Tells you which application is communicating. Sequence and acknowledgement numbers used to confirm packet delivery. Flags show connection states. Example, when you open a website, the first 3 packets are a TCP handshake, SYN, arrow, SYNA, CK, arrow, ACK. You can spot these in Wireshark by filtering. tcp.flags.syn equals 1, that's how you detect connection attempts. For UDP example, User Datagram Protocol, SRC port, 42,717, DEAST port, 53. UDP, unlike TCP, doesn't care about reliability, it just sends data quickly. It's used in streaming, DNS, and gaming traffic. You'll mainly see source and destination ports, no sequence numbers or acknowledgements. Try filtering UDP packets using UDP. Then notice how light and fast they appear compared to TCP. 4. Payload, Layer 7, application data. Finally, this is the payload, the actual content being transmitted. For HTTP, this might be text, headers, or a web request. For DNS, it's the domain name query. For encrypted traffic like HTTPS, this section will look like random bytes because it's encrypted. In a lab, when traffic isn't encrypted, you can actually read what was sent. But in real-world HTTPS sessions, you'll need decryption keys, and we'll cover that in a later episode. Part 3. Hands-on example, mapping the layers. Let's make this real. I'll open my browser and visit test.php.voolnweb.com. Stop the capture and filter for HTTP using HTTP. Now expand it. Ethernet. My Mac talking to the router's MAC IP. My local IP sending to testphp.voolnweb.com's server. IP TCP. My computer using port 56,176. Destination port 80. HTTP. HTTP. The actual GET request for the web page. And there it is, the full journey of a packet, from hardware to human-readable content. Part 4. Why this matters. Understanding packet structure makes you more than a Wireshark user. It makes you a network detective. Whether you're investigating malware, analyzing latency, or reverse engineering network traffic, this knowledge is your foundation. Part 5. Wrap up and hook. For Part 5. Congratulations! You now understand the anatomy of every packet that moves through your network. In the next episode, we'll go beyond structure and learn how to follow TCP streams and reassemble sessions, meaning you'll be able to see entire conversations, from HTTP logins to file transfers, reconstructed live inside Wireshark. Part 5. Follow TCP streams and reassemble sessions, HTTP, SMTP, FTP, Wireshark Lab. Welcome back, network hunters. Until now, we've learned to capture packets, filter them, and understand their structure. But what if you could read the full conversation hidden inside those packets? Today, I'll show you how to follow TCP streams and reassemble sessions, the skill that separates amateurs from true Wireshark professionals. Part 1. What is a TCP stream? When two devices communicate using TCP, data is broken into multiple packets. Each packet is just a piece of the full message. Wireshark can gather those pieces and rebuild the complete conversation. That's called following the stream. For example, when you open a website, you send multiple TCP packets carrying your request, and the server replies with several packets carrying the response. Wireshark can combine those pieces back into readable text. Part 2. Follow a TCP stream, HTTP example. Start capturing. Visit any non-HTTPS page, then stop the capture. Filter for HTTP traffic using HTTP. Now right-click any HTTP packet and choose Follow TCP Stream. Boom! This window shows the entire HTTP conversation, request and response together. The red text is what your computer sent. The blue text is what the server replied with. Scroll through it. You'll literally see headers like GET, HOST, User Agent, and even HTML content of the web page. You can also save this stream as a .txt file for deeper analysis. Part 3. SMTP email. Example: if you capture traffic from an unencrypted email protocol such as SMTP, POP3, or IMAP, you can follow the same method. Filter SMTP traffic using :SMTP. Then right-click any packet, follow TCP stream. You'll see the raw conversation between your email client and the mail server. Of course, in modern secure setups, this data is encrypted with TLS, but in lab environments, it's a perfect way to learn protocol behavior. Part 4. FTP file transfer. Example: now let's look at FTP, the file transfer protocol. Start a small lab with an FTP server, or use a capture file. Filter FTP traffic using :FTP. Then follow the TCP stream. You'll see login commands like user and pass, then directory listings and file transfers. This is how investigators can detect insecure file transfers, because the credentials are visible in plain text. Part 5. Reassembling sessions. Wireshark doesn't only rebuild text conversations, it can also reassemble binary sessions like files or images. For example, when you download a file over HTTP, Wireshark captures all its packets. You can extract the file by choosing File Export Objects, HTTP. Here, you'll see every file that passed through: HTML pages, images, scripts. Select one, click Save, and Wireshark will rebuild it from the captured packets. This is extremely useful for forensics and malware analysis. Part 6. Wrap up and next episode. Hook. You've now learned one of Wireshark's most powerful features: following TCP streams and reconstructing full sessions. In the next episode, we'll take it even deeper. Decrypting TLS when you own the keys, and analyzing HTTPS traffic safely inside your lab. That's the gateway to mastering secure communications analysis. Subscribe, stay focused, and keep sniffing those packets. Part 6. Decrypt HTTPS TLS in Wireshark. Real decryption workflow. Most people think HTTPS traffic is completely invisible. But inside your own lab, when you control the keys, you can actually decrypt it. Today, I'll show you exactly how professionals analyze encrypted traffic ethically inside Wireshark. Part 1. Quick recap: what is HTTPS/TLS? HTTP is plaintext. Anyone can read it. HTTPS is HTTP plus TLS, transport layer security. TLS encrypts data between your browser and the server. But if you own the keys, or capture from a client where you can log session secrets, you can unlock it. The goal of this lab is to decrypt HTTPS packets using session keys. Totally legal, totally under your control. Part 2. Setting up the lab. You'll need 3 things. 1. Wireshark, latest version. 2. A browser, Chrome or Firefox. 3. A simple HTTPS website to test. Even HTTPS, example.com works. We'll make our browser save the session keys to a file, then Wireshark will use that file to decrypt everything. Part 3. Capture TLS traffic. Start Wireshark and begin capturing on your main interface. Visit any HTTPS site, maybe log in or refresh a page, then stop the capture. Notice these packets say client hello, server hello, application data. You can't read the content yet. It's encrypted. Part 4. Exporting session keys. So keylog file. Now, here's the secret weapon. Modern browsers can export the encryption keys to a log file. In Chrome or Firefox, do this. Windows command, PowerShell, setx, SSLKEYLOGFILE, %user profile, %desktop, %SSLkeys.log. Close and reopen your browser after running this. It'll start saving session keys every time you open HTTPS websites. Part 5. Decrypt in Wireshark. Go back to Wireshark. Navigate to Edit Preferences Protocols, TLS, under Pre-Master Secret Log File, name, browse and select your SSLkeys.log file. Click OK and reopen your capture. Now watch the magic. The HTTPS traffic is suddenly readable. Boom! You can see HTTP requests, responses, even JSON data, all decrypted inside Wireshark Part 6. Important notes: only decrypt traffic you own or have permission to analyze. Never try to decrypt someone else's traffic. That's illegal. This method is meant for cybersecurity research, debugging, and penetration testing inside your own lab. If the website uses TLS 1.3, most do, this method still works perfectly, as long as the browser writes the session keys to that log file. Part 7. Bonus. Decrypting packet captures from tools. You can also use this trick with captures from curl, Python requests, or Postman. Import requests, requests.get, https example.com. Verify equals false. As long as you have the keys, Wireshark can decrypt the session. Part 8. Next episode. Teaser. You just unlocked encrypted traffic, a skill that 95% of analysts never master. In the next part, we'll go even deeper. Analyzing malware, HTTPS traffic. How to tell if encrypted traffic hides a threat. Subscribe, stay sharp, and keep sniffing like a pro. Part 7. Find malware and see inside HTTPS. Wireshark Behavioral Analysis, GUI. Most people believe encrypted traffic is safe because it's unreadable. That's half true. You can't read the payload, but you can read the behavior. Today, I'll show real techniques to spot malware command and control, C2, and suspicious callbacks inside HTTPS using only Wireshark's GUI and smart analysis. Let's catch ghosts hiding behind Encryption 1. Ethical and safety reminder. This is an educational ethical lab. Only analyze traffic you own or have written permission to inspect. Do not attempt to intercept or decrypt third-party traffic. If you find malware in a production network, isolate the host and follow your incident response procedures. 2. What you can see in TLS/HTTPS TLS handshake metadata. Client, hello, server hello, certificate. SNI, server name indication, host name in clear. Packet timing, sizes, and directionality. Behavioral signals. Connection frequency and patterns. Beaconing. Certificate anomalies. Self-signed. Wrong CN. Short validity. TLS version / cipher choices and renegotiation behavior. 3. High-level detection strategy. Find candidates. Identify encrypted flows to unusual hosts or ports. Profile behavior. Periodicity, jitter, small consistent payloads, beacons. Inspect TLS metadata. Unusual SNI, weak ciphers, certificate mismatches. Correlate with DNS and endpoints. Suspicious domains, new external IPS, parent/child processes if you have endpoint data. 4. GUI workflow. Step-by-step, yes. Step A. Identify external TLS flows. Filter TLS and IP.addr not equal to 192.168.1.0/24. Replace 192.168.1.0/24 with your local network. Paste that into the top filter bar. Enter. This filters TLS flows not originating in the local LAN. You want external connections that could be C2 callbacks. Step B. Sort by packet count / bytes. Find low-volume persistent flows. Menus, statistics, conversations, TCP click packets, or bytes to sort. Look for small but persistent flows, low bytes, many packets, or connections that repeat at regular intervals. These are classic beacon patterns, regular tiny check-ins to a C2 server. Step C. Timeline and I/O graph. Visualize periodicity, statistics, I/O graphs. Add a graph with filter set to the suspect flow, e.g. TLS and IP.address equals 13.107.3.128. Use y-axis equals packets, x equals time. Look for evenly spaced spikes, beaconing. Periodic spikes every x seconds is a red flag. Step D. Drill into handshake metadata, SNI, certs, ciphers. Filters to use: show client, hello packets, TLS, handshake, type equals 1. Show server name, SNI. For client, hello, TLS, handshake, extensions, server name. Step E. Check packet sizes and directionality. Filter for single flow analysis. IP.addr equals 13.107.3.128 and in TCP.port equals 443. Look at the info column and packet bytes to see. Small TLS application data from client to server and small responses back. Typical beacon: client sends approximately 100 bytes regularly, server replies small ACKs or tiny payloads. Summary filter to find small application data, TLS packets, TLS.record.content type equals 23 and frame.len less than 300. This finds TLS application data records under 300 bytes, useful to find many small encrypted messages. Outro. There you go. Strong, practical methods to find malicious activity hiding inside HTTPS without decrypting it. Smash like if you learned something dangerous, ethically. Subscribe for Part 8. Part 8. Advanced Capture, Filters. Save disk and capture only what matters. Millions of packets, zero time to analyze. Capture filters let you stop the flood at the source. In this short video, I'll show the exact capture filters pros, paste into Wireshark so they only record the packets that matter. Save disk, save time, and find the needle instantly. Let's go. Quick reminder: capture versus display filters. Two kinds of filters. Capture filters run while capturing. They decide what gets written to disk. libcap/bpf syntax. Display filters run after capture. They decide what you see in Wireshark. Wireshark syntax. Today is about capture filters, the ones that stop useless packets from ever being saved. Open Wireshark. Click Capture, Options, or click the gear icon next to an interface. In the Capture Options dialog, find the Capture Filter field text box. Paste your capture filter there and click Start. Or, from the welcome screen, click the little filter text box under the interface name. Some builds show a quick capture filter. Capture filter basics. Syntax reminder. Capture filters use libcap/BPF syntax. Operators are English-like, and or not. Fields are like host, net, port, TCP, UDP, ARP. Always use capture filters when you want to reduce file size or capture only relevant traffic. 1. Capture only traffic to from one host, host 192.168.153.100. What it does, record packets where source or destination equals 192.168.153.100. Use when you care only about one device. 2. Capture only traffic from a host, source only, SRC host 192.168.153.100. What it does, capture only packets originating from that host. 3. Capture only traffic to a host, destination only, Ds to host 192.168.153.100. Capture a whole subnet/network net 192.168.1.0/24. What it does, capture traffic where source or destination is inside that IPv4 subnet. Great for LAN captures. 5. Capture only TCP traffic, all TCP use. When you only want connection-oriented traffic, HTTP, SSH, etc. 6. Capture only UDP traffic, UDP 7. Capture only DNS, UDP usually port 53, port 53 or more strictly, UDP port 53, use when you want DNS queries and responses only. 8. Capture only HTTP port 80, TCP port 80. Note: HTTPS uses port 443. To capture TLS handshake, you'd use TCP port 443. 9. Capture only HTTPS, TLS. Traffic, only port filtering, TCP port 443. Important, you will capture encrypted traffic. Payload will be unreadable without keys, but this reduces noise. 10. Capture only traffic to a set of ports. Port list, TCP port 22, or TCP port 80, or TCP port 443 short form with parentheses, recommended, TCP, and port 22, or port 80, or port 443. 11. Capture a port range. Port range 1024 to 2048. Use when you want ephemeral ports or a service range. 12. Capture only ARP, link layer, ARP. 13. Capture only ICMP, ping, traceroute, ICMP. 14. Capture only traffic on a VLAN, 802.1q, LAN 100, or VLAN plus host, LAN 100, and host 192.168.153.10015. Capture only broadcast or multicast. Broadcast, broadcast, multicast, multicast. 16. Capture by MAC address, Ethernet, Ether, host, 00:11:22:33:44:55. Use when you want hardware-level device capture on the local LAN. 17. Negation. Exclude traffic, not. Example, capture everything except MDNS/Apple TV noise, not port 5353, combine with host 192.168.153.100, and not port 535318. Combine host plus port capture only HTTP to host 192.168.153.100 and TCP port 8019. Complex example, capture DNS plus HTTP, but only from a host, SRC host 192.168.153.100 and UDP port 53 or TCP port 8020. Small advanced BPF example, capture SWIN packets only, connection attempts, TCP open bracket 13, close bracket ampersand 0, x02, not equal 0. What it does, matches TCP packets where the SYN flag bit is set. connection attempts. Warning: advanced BPF syntax. Test it and only use if comfortable. 21. Capture only traffic matching multiple IPs. Set host 192.168.153.100 or host 10.0.0.6 or host 10.0.0.7. Better, if supported, use multiple ORs. Capture filter sets are not available for IP.ADIA, like in display filters. Quick real-world recipes. Paste these as single lines in capture filter. Only capture your workstation, talking to web servers. Host 192.168.153.100 and TCP port 80 or TCP port 443. Capture DNS and DHCP for troubleshooting, name resolution. UDP port 53 or UDP and port 67 or UDP and port 68. Capture only traffic between two hosts. Host 192.168.153.100 and host 10.0.0.2. Capture only traffic. Not internal. Exclude local subnet, not net1, 9, 2.16, 8.1.0/24, safety and ethics. Always run captures only on networks you own or where you have written permission. Capture filters don't make it legal to record other people's traffic. Get consent, redact sensitive info, and follow your org's policy. Outro and CTA. That's your capture filter masterclass. Want the file? Comment, capture please. Try them in your lab. And don't forget to like and subscribe, my king. Part 9. Advanced display filters and automated searches. Wireshark profiles. If you can't find the packet you need in 60 seconds, you're doing it wrong. In this episode, I'll teach you display filter, so you can hunt bugs, trace attackers, and debug networks faster than 99% of analysts. Copy, paste, and go live. Let's level up 1. Quick recap. Where to type filters. The display filter bar is the top input in Wireshark. Type filters there and press enter. Use the expression button to build fields with a UI if you don't remember syntax. Wireshark auto-completes fields. Use tab to accept suggestions. 2. Powerful filter patterns. A. Host/IP focused. Show only traffic to slash from a host. IP.adder equals 192.168.160.100. Show traffic from a specific source. IP.src equals 192.168.160.100. Show traffic to a destination. IP.dst equals 8.8.8.8b. Port service focused. All traffic where either side uses TCP port 443. TCP.port equals 443. Only client, server, destination, port 80. TCP.dst port equals 80C, combined by host plus protocol, useful for targeted analysis. Show HTTPS traffic involving 192.168.160.100:IP.ADR equals 192.168.160.100 and TCP.port equals 443D. Protocol fields and logical expressions show HTTP post requests to GISH login, http.request.method equals post, and http.request.uri contains //login. Show TCP SYNs that start connections. TCP.flags.syn equals 1 and TCP.flags.ack equals 0. Show TCP retransmissions, TCP.analysis.retransmission E. Use parentheses to group logic. Show TCP traffic to host A or UDP to host B. IP.adr equals 192.168.160.100 and TCP. Or IP.adr equals 192.168.160.100 and a not TCP. 192.168.160.100 .160.23, and UDP-F. Negation, exclude noise, exclude MDNS and ARP, broadcasts, cleanup, LAN, noise, exclamation mark, MDNS, WH, ARP, G, range, and set operators, show TCP ports in a set. TC.port in 22, 84, 43, 3389. H, field comparisons and numeric ops, show frames greater than 1500 bytes. Frame.len greater than 1500 I. Outro and next steps. You've just learned how to slice through millions of packets and find the one you need using filters. In the next video, we'll apply these tools to real network troubleshooting, latency, retransmissions, and TCP problems. And I'll show you the exact filters and graphs pros use to fix network slowness. Don't forget to like and subscribe so you don't miss the next lesson. Part 10, Troubleshoot Network Latency and TCP Issues, Wireshark GUI Guide. Users say the internet is slow, but where do you start? In this episode, I'll show you step-by-step how to pinpoint latency, packet loss, and TCP problems using only Wireshark's GUI. By the end of this video, you'll know exactly which packets to blame and how to explain the fix to your boss. What you will learn: how to spot retransmissions and duplicate ACKs, how to measure round-trip time, RTT, and time gaps, how to interpret TCP window issues and throughput limits, exact GUI steps, graphs, and copy-paste display filters you can use live. Part 1. Start with a focused capture. Always start with a capture that includes the problem. Limit capture noise with a temporary capture filter in capture options, like host 192.168.15.3.100, where 192.168.153.100 is the problem host. This keeps the file small and focused. Part 2. Use expert information, fast triage, GUI steps, analyze expert information. This view highlights problems, warnings, notes, retransmissions, duplicate ACKs, zero window, etc. Sort by severity, start fixing the red items first. Common expert entries to see: TCP retransmission, TCP previous segment not captured, TCP DUPACK, TCP zero window. Part 3. Key display filters all: TCP retransmissions, TCP.analysis.retransmission, fast retransmissions, TCP.analysis.fast_retransmission, duplicate ACKs, TCP.analysis.duplicate_ACK, zero window receiver, can't accept more data, TCP.analysis.zero_window, TCP reset RST packets, TCP.flags.reset equals 1. TCP connections with retransmits and a specific host, TCP.analysis.retransmission, and an IP.adder equals 192.168.153.100. Replace 192.168.153.100 with your host IP in each demo. Part 4. Find the top problematic streams, GUI steps, statistics conversations. TCP sort by packets or bytes to find top talkers. Click a suspect conversation, apply as filter selected. Wireshark will create TCP.stream equals X. Filter example TCP.stream equals 7. Use TCP.stream to isolate one connection and analyze behavior in detail. Part 5. Time sequence, TCP trace, and RTT graphs, GUI steps, statistics, TCP stream. Graphs, time sequence, Stevens, shows sequence numbers versus time. Retransmissions show as overlapping segments. Useful to visually spot where gaps and retransmits occur. RTT, graphs, statistics, TCP stream. Graphs, round-trip time. Use this to see measured RTT over time. Spikes equals network latency. Part 6. Zero window full. Receiver can't accept data. Symptoms: tcp.analysis.0_window entries or tcp.window_size equals 0 in packets. Root causes and fixes. Receiver overloaded or memory pressure. Investigate process on host. Application back pressure. Tune server. Side buffer sizes. Filter. tcp.window_size equals 0 or tcp.analysis.0. Window outro. CTA and next episode teaser. You just learned to find the real cause of network slowness, retransmits, window problems, and latency using only Wireshark. Smash that like, subscribe, and comment. Report please. If you want me to auto-generate a troubleshooting report template, you can drop into Incident. Part 11, Threat Hunting with Wireshark, Traffic Indicators, and IOC Detections. Most people think HTTPS hides everything. It doesn't. It only hides the content, but not the behavior. Today, I'll show how to find malware hiding behind encryption using Wireshark's GUI and a few smart filters. If you want to catch attackers by their traffic, watch every second. This is an educational demo using simulated malware in a lab. Always get written permission before capturing or analyzing other people's traffic. Let's stay legal and ethical setup. And what you can see, open your PCAP file or start a live capture. You can't read encrypted data, but you can read TLS metadata, client, hello, SNI, certificates, DNS queries, and answers, packet sizes and timing direction and duration of connections. These are breadcrumbs that threat hunters follow to trace hidden malware. Hunt 1, DNS, find suspicious domains. Filter 1, DNS shows all DNS traffic, requests, and responses. Used to detect domains queried by infected hosts. Malware often uses DNS for command and control or domain generation algorithms. Filter 2, DNS.QRY.name matches 0 to 9, A to Z16, finds long random domain names. Detects algorithmically generated domains used by advanced malware. Filter 3, whitelist noise reduction, DNS and not DNS.QRI. .name contains Google and not DNS.QRI. .name contains Microsoft and not DNS.QRI. .name contains Cloudflare. Removes common safe domains to focus on suspicious or rare ones. Right-click any packet, apply as column DNS.QRY.name. If you see many lookups for long random names, that's a DGA signature. Hunt 2, HTTP, suspicious posts and payloads. Filter 4, HTTP.request shows all HTTP requests, get and post. Used to see all HTTP requests from clients to servers. Filter 5, HTTP.request.method == post. Shows only post requests. Post often used by malware to upload stolen data. Filter 6, HTTP.user_agent contains Python. Finds suspicious automated clients. Detects programmatic clients like Python scripts or malware beacons. Hunt 3, TLS/HTTPS metadata analysis. Filter 7, TLS shows all TLS/SSL traffic. Reveals encrypted connections without decrypting content. Filter 8, TLS.handshake.type =1. Shows client hello packets. Used to identify client negotiation and initial TLS handshake. Filter 9, TLS.handshake.extensions_server name displays. SNI host names shows the host name clients connected during encryption setup. Filter 10, TLS record.content type =23 and frame.len less than 300 finds very small application data packets. Used to detect small repetitive beacons. Typical malware heartbeat. Outro plus call to action. That's how you hunt malware hidden inside HTTPS. You don't need decryption, you need intuition and observation. In the next episode, we'll automate this using TShark, turning these manual filters into smart detection scripts. Please like, subscribe, and I'll see you in the next lab. Stay sharp, ethical, and unstoppable. Part 12, TShark CLI Tutorial, Wireshark from CLI, Beginner to Pro. Most people think Wireshark is only for GUI lovers, but let me shock you today. This is TShark, the command line version of Wireshark, and it can do everything from capturing live packets to filtering, analyzing, and exporting network data, all without opening a single window. In this video, I'll take you from beginner to pro, step by step, and by the end, you'll master every powerful feature that real network analysts use in the terminal. So grab your system, open your terminal, and let's turn you into a Wireshark CLI expert. Section 1. What is TShark? So first of all, what exactly is TShark? TShark is the command line interface of Wireshark. It's built by the same developers and uses the same engine, the libcap library, for packet capturing. The difference is Wireshark GUI for visual analysis, TShark CLI for automation, scripting, and working on remote servers. You can think of TShark as Wireshark without graphics, but with superpowers. Section 2. Installation. Now let's start by installing TShark. On Linux, Debian, Ubuntu, sudo apt update sudo apt install TShark. Y on Fedora or CentOS, sudo dnf install Wireshark CLI, Y, and on Windows, it's already included when you install Wireshark. You can open CMD or PowerShell and type TShark-V. If you see the version number, congratulations, TShark is ready to go. Section 3. Capturing packets. Let's start with live capture. To list all available network interfaces, use TShark-D. This shows you all network interfaces, like Ethernet, Wi-Fi, or any virtual adapter. To start capturing on a specific interface, use sudo tshark-i1. The -i1 means interface number 1 from the list. Press Ctrl+C to stop capturing at any time. Section 4. Capture filters. Sometimes you don't want to capture everything. For example, to capture only HTTP traffic, sudo tshark-i1 ftcp port 80. Or to capture only traffic from a specific IP, sudo tshark-i1 f host 192.168.153.100. These are called capture filters, and they're applied before the packets are saved, meaning faster and cleaner captures. Section 5. Display filters. Display filters help you analyze packets after capturing. Example, shark-r capture.pcap-y HTTP, or show only packets where IP equals a specific address, shark-r capture.pcap-y IP.adir equals 192.168.153.100. Display filters are super powerful. You can use almost any Wireshark filter syntax here. Section 6. Saving captures. You can save your live capture into a .pcap file. Sudo tshark-i1-w mycapture.pcap. Then later, you can open it with Wireshark GUI or analyze it again with tshark-r mycapture.pcap. Section 7. Extracting fields. TShark can extract only the information you need. For example, just the IP addresses and protocol names, shark-r capture.pcap-t fields eip.src-eip.dst-e_ws.col.protocol. Section 8. Statistics and analysis. Let's move to the fun part. Statistics. To get protocol hierarchy, shark-zio, phs-r and capture.pcap. To see conversation list, who talked to who. Shark-z-conv, ip-r capture.pcap. To view top talkers, most active hosts. Shark-z endpoints, ip-r capture.pcap. Section 9. Real world. Example. Let's do a real example. I'll start capturing traffic while I visit a website. Sudo shark-h1-f TCP port 80-W website.pcap. Then stop after a few seconds. Now I'll analyze it. Shark R website.pcap. Y http.request. You'll see get and post requests, host names, and even URLs, all directly from the terminal. That's pure power. Section 10. Bonus. Combine with grep and automation. You can combine TShark with Linux tools like grep, awk, and cut for automation. Example: TShark R capture.ptap, tfields, eeip.src, sort, unique, c. This command shows unique IPs and how many times they appear. Perfect for quick network summaries. Outro, and that's it. You've just mastered TShark, the command line Wireshark used by professional network engineers and ethical hackers worldwide. If you found this helpful, don't just leave, subscribe, like the video, and comment Wireshark CLI Master so I know you finished the full tutorial. This is your boy, ACW360, and I'll see you in the next deep dive network analysis episode. Part 13, PCAP Forensics, Merge, Analyze, and Chain of Custody, PCAP/PCAPng. Anyone can capture packets, but a professional knows how to preserve them. In this lab, we'll treat every packet like digital evidence. You'll learn how to merge multiple captures, rebuild missing sessions, verify file integrity, and maintain a legal chain of custody, all inside Wireshark. This is the difference between a hacker and a forensic investigator. Scene 1. The power of PCAP. When you capture packets in Wireshark, everything you see, IPs, ports, timestamps, payloads, is stored in a .pcap or .pcapng file. These files are your digital evidence containers. Think of them like security camera footage of your network. If you know how to manage them properly, you can go back in time and prove exactly what happened. Open Wireshark file, save as, select .pcapng.pcapng, supports extra metadata comments, interface info, etc. Scene 2. Capture file types. Wireshark mainly uses two formats. One, PCAP, the classic format, simple, compatible with older tools like TCP dump. 2, pcapng, the modern version, supports multiple interfaces, annotations, name resolution, and more. Always prefer .pcapng unless you specifically need compatibility with old systems. Scene 3. Merging multiple captures. Sometimes you capture traffic on multiple interfaces or at different times. Wireshark can merge them into a single timeline automatically. Mergecap-w merged.pcapng, capture 1, .pcapng, capture 2, .pcapng. Mergecap is part of Wireshark. W specifies output file. You can merge two or more files. Optional, sort by timestamp to avoid confusion. Editcap-t0 merged.pcapng, sorted_merged.pcapng, then open sorted_merged.pcapng. In Wireshark, check timeline, continuity. Scene 4. Splitting large captures. If your capture is too large, Wireshark can slow down. Use EditCap to split it into smaller parts for analysis or archiving command. EditCap C50,000 bigcapture.pcapng split output.pcapng splits every 50,000 packets into new files. Or split by time, EditCap I 300 bigcapture.pcapng split 5 minutes.pcapng splits every 300 seconds. Scene 5. Removing corrupted or sensitive packets. If your capture has private or corrupted frames, you can remove them safely before sharing with your team. Command examples. Remove packets 1 to 20, EditCap, rcapture, capng, clean, capture, papng 1 to 20. Remove specific frames like 100, 250, 400 EditCap, rcapture.pcapng to clean_capture how.pcapng 100, 250, 400. Always sanitize sensitive traffic before uploading or sharing, especially if it contains credentials or private IPS. Scene 6. Adding comments and annotations. PCAPng files allow you to add comments to frames. Perfect for evidence documentation. In Wireshark GUI, right-click any packet comment, write a note. Save file again. These comments can describe what you saw, timestamps, analysis notes, or investigation results. Later, another analyst or court can read them directly in the capture. Scene 7. Verifying integrity. SHA-256 hash. Once you have your clean capture, hash it. The hash proves the file hasn't been modified since you saved it. A critical step for forensic integrity. Command SHA-256 sumcapture.pcapng greater than capture.SHA-256. Verify later SHA-256 sum-c capture.SHA-256. If the file ever changes even 1 byte, the hash won't match. Proof that the evidence was altered. Scene 8. Ethical reminder. Forensics is powerful. You can see who connected, when, and what they sent. Always capture responsibly on networks you own or have written permission to analyze. Use your skills for investigation and defense, never invasion. Scene 9. Outro. Now you've reached investigator level. You can merge, split, sanitize, hash, and document captures like a professional forensic analyst. In Part 13, we'll enter the real-world lab, capturing a web session, analyzing authentication flows, and revealing a plaintext password. Ethically, of course. Like, share, and drop a comment. Part 14, Real Lab, capture web login and reveal plaintext password. DVWA. You've seen Wireshark capture packets, but can it really reveal usernames and passwords from a real web app? In this ethical lab, we'll use DVWA, the world's most famous vulnerable web app, to capture a real login and expose the credentials inside Wireshark. Let's go. Ethical warning. This is a controlled lab. Everything you'll see here happens inside a virtual environment. No public networks, no unauthorized testing. Wireshark is a powerful tool. Always use it ethically and legally. Step 1. Launch DVWA. If you're using Kali or any penetration testing VM, DVWA usually comes pre-installed inside the Metasploitable 2 or XAMPP DVWA package, then open browser, then go to http://192.168.153.23/dvwa/login.php. Default credentials, username, admin password, DVWA runs on HTTP, not HTTPS, which makes it perfect for a lab like this. Anyone capturing traffic can see the login data. Step 2. Start Wireshark capture, open Wireshark. Choose your active interface, usually ETH0, WLAN0, WLP2, S0B1, or low if local. To reduce noise, set a capture filter before starting. Host 1, 92.168.153.23 and port 80, or if on localhost, host and port 80, start capture. Now Wireshark is listening. Anything we send over port 80 will be visible. Step 3. Perform the DVWA login. In your browser, open http://192.168.153.23/dvwa/login.php, enter. Username, admin, password, then click Login. You'll see DVWA load its dashboard page if successful. That's the moment we've been waiting for. Let's stop the capture and go hunting inside Wireshark. Step 4. Analyze packets filter, HTTP requests. In the Wireshark filter bar, http://request, press enter. You'll see get and post requests. Look for post/dvwa/login.php/1.1. This is the login request, exactly where the credentials are sent. Step 5. Inspect the POST packet. Click the POST packet. Expand Hypertext Transfer Protocol in the middle pane. Look for username equals admin and password equals password and login equals login. There it is, both username and password, fully visible. This is the real danger of HTTP. Step 6. Follow the TCP stream. Right-click the post packet, follow TCP stream. You'll see post/DVWA/login.php http/1.1 host:192.168.153.23 ... username equals admin ampersand password equals password ampersand login equals login quote. This shows the entire HTTP request quote and response conversation. Red is what the client sent, blue is what the server replied. You can literally read the password in plain text. Step 7. Export and save evidence, 7:30-9. If you want to save this demo, go to File Export, Specified Packets, Selected Packets, only save as DVWA_login.pcapng. You can also export the TCP stream text, follow TCP stream. Save as DVWA_stream.txt. Then hash your files for evidence, integrity, SHA-256, some DVWA_login.pcapng greater than DVWA_login.SHA-256, SHA-256, some DVWA_stream.txt greater than DVWA_stream.SHA-256. In digital forensics, hashing is used to prove the evidence file hasn't been altered. An important step in real investigations. Why it happens. HTTP transmits data as plain text. That's why we can read credentials like this. HTTPS encrypts everything using TLS. So tools like Wireshark would only see encrypted gibberish instead of readable text. Quick checklist. DVWA running on HTTP, not HTTPS. Wireshark capturing port 80. Filter. HTTP request method equals post. Right-click follow TCP stream. Found username and password, export.pcapng and .txt. Outro. You just watched Wireshark expose a real login from DVWA, step by step, ethically and clearly. In the next and final part, we'll wrap up this Wireshark Mastery series with a real-world challenge and a teaser for the Metasploit series that's coming next. Like, subscribe, and get ready for the finale, my unstoppable king, because the next one will connect Wireshark with live exploit traffic. Part 15, Wireshark series finale, key takeaways, and what's next. Wow, we did it. From installing Wireshark to decrypting HTTPS, following TCP streams, and even hunting malware, you've just completed one of the most complete network analysis series on YouTube. You didn't just learn to use Wireshark, you mastered it. 1. I want to pause for a second and say thank you from my heart to every single one of you who watched, liked, commented, and subscribed during this journey. You didn't just support a channel, you built a community of cyber defenders, people who want to understand what really happens inside the network. You are now part of that elite group too. Celebrate their journey. Think about it, my King's Army of analysts. In Part 1, you learned what Wireshark really sees. In Part 2, you installed it and learned how to capture your first packets. In Part 4 and 5, you mastered display filters and packet structures. In Part 6 and 7, you followed TCP streams and even decrypted TLS. In Part 9 and 10, you learned real troubleshooting and malware detection. And now, you've reached the final stage, a true network forensic analyst. That means you've gone from beginner to professional in one full masterclass series. You can now capture, filter, and analyze any network traffic, rebuild sessions and extract evidence, detect malware indicators and encrypted tunnels, use filters faster than 90% of analysts online. That's not basic knowledge, that's professional skill. But remember, This isn't the end. If you thought Wireshark was deep, the next series will blow your mind. Metasploit Framework, Full Exploitation Course, Deep Packet Analysis Labs, Real Attack Traces, Phishing and Social Engineering Defense Series, Bug Bounty Hunting Roadmap. This channel is not for entertainment, it's for transformation. From beginners into cyber kings and queens. So before you go, do 3 things right now. 1. Smash the like if this Wireshark series helped you grow. 2. Subscribe plus bell icon because the next series starts soon. 3. Share this playlist with your friends because knowledge grows when shared. Let's fill the world with smarter defenders, not just users. Always remember this. Wireshark is not just a packet sniffer, it's a window into truth. You now see what others can't. You can read the language of the network. This is ACW360 signing off from the Wireshark Masterclass. But our mission doesn't stop here. Next stop, Metasploit, where we move from listening to the network to controlling it. Stay sharp, stay curious, and always stay legendary.